Okay, recording has started. So, good morning, everybody. Welcome back to Math 115. So, today we're going to continue our discussion about graphs of trigonometric functions, and we are hopefully going to finish up that topic today and start in on what we were supposed to start yesterday, which is inverse trigonometric functions. Okay, so before we start, let me remind us of where we were last time. So let's see. At the start of last time, we kind of reviewed what we had been talking about. This is office hours, which is how we graph these trigonometric functions. And this was a really nice diagram that was in the book that I really liked about it. And essentially what we are going to do is we're going to let's see if this, no, that does not show up. We're going to let this purple hand of our clock here, basically, we're going to let this go around. Okay, and as this goes around, we're going to take note of one of the values of the point on the unit circle which this purple hand crosses through. Okay, and depending on whether we're talking about sine or cosine, then we're going to, as the angle marches forward, we're going to march forward on the x-axis, and the height of the graph, if it's sine, is going to correspond to the height of the point on the unit circle, which corresponds to that angle measurement in radians. Okay, or if it's cosine, then the height of the function is going to correspond to the x value of the point on the unit circle, which corresponds to this angle measurement, okay, as we go around and around and around. And since this is a process which is pretty much going to repeat as we make it back around to 2 pi, well, as we go from 2 pi to 4 pi, the process is going to be the same as when we went from 0 to 2 pi. So we call this periodic. And the way it manifests in the graph is after we see this first section of the graph here, it's going to repeat like this over and over and over again. Okay, so that was periodicity in the graph. And then we talked a little bit about amplitude and period. Okay, if you want to hear a little bit more about that, I did some office hours after class yesterday that are recorded there on the YouTube channel. So if you didn't catch those, there's more on period and amplitude there. And then I think almost the last thing we talked about was phase shifts, okay, which is just the weird word that we use to describe a horizontal shift of a periodic function, okay, or a trigonometric function. All right, and one kind of interesting fact that we noticed here was that if we phase shift sine or cosine by the length of the period, okay, then we wind up with a graph which looks like exactly like our original graph. Okay, exactly like our original graph, and it will just lie on top. But this is kind of by virtue of the fact that it's repeating over and over and over again. So it's kind of like, well, I don't know what it's like. I mean, I guess it's like, the ocean, if you're standing on this wave and you look left and right, well, you see kind of the same thing as if you were standing on this wave. I guess that's one way maybe you could think about it. Okay, so that's another sort of consequence of the periodicity. Okay, and then the last thing we talked about was finally, okay, let's put this all together and let's graph one of these really, really kind of bad looking trig functions. Okay, so this one had a vertical stretch, a horizontal stretch, a horizontal shift, a y-axis reflection. I think that's it. No vertical shift. Okay, and the way we do this is just start with the graph of cosine. Okay, so we start with the graph of cosine, and then we apply the transformations in the same order that we applied transformations way back when we learned function transformations from parent functions in like the first couple weeks of class. Okay, so we do a horizontal shift, then stretches and compressions, reflections, and then finally the vertical shift. Okay, and this is the order that we do these in. Sometimes you can get away with permuting a couple of those, but I always forget which ones they are. So this is the list that the book gives, so that's what I'm following. And so we kind of wound up with this graph here, which, of course, I didn't draw enough of the left side of the x-axis to make this picture look really good. But we wound up with something like this, and we checked our work by checking, well, it looks like this function is reaching a maximum when x is equal to pi. So we can try, where did it go? Oh no, sorry. The way we did it was the other way. We said it looks like this function should reach a minimum when x is equal to negative pi. And since we know this function should have a minimum of -3, we could check and make sure that when we plug in x equals negative pi into our function here, that we get something on the inside which is going to evaluate to a point at which cosine takes a minimum value. Okay, and we did that, and it turns out that it was true. So that's kind of one way that you can check and see if your graph is good. Okay, you can always check and see if a point on your graph, when plugged into the equation, gives you what you thought you should get. Okay, and then we had a GIF break, and then we were gonna go talk about something else, which is the graphs of all of our other trigonometric functions. Okay, so this is the last thing that we talked about yesterday, was how do I graph something like tangent of x? Okay, and the principle, like all of the other trigonometric concepts that we've learned regarding tangent and cotangent and cosecant and secant, okay, it relies basically on a manipulation of what we already know about sine and cosine. Okay, so let me clean this up a little bit and say a bit more about this. So what we said we were going to do is, well, okay, if we want to graph tangent for a given point, so let's consider this this yellow highlighted region here. Okay, so this x value, which corresponds to pi over 2. Okay, so x value of pi over 2. Well, if we want to know what does the graph of tangent look like at that point, oh well, maybe I shouldn't have chosen that point. Let me instead focus on this point here. Instead, focus on this x value, which I've highlighted in this region. Well, if we want to know what does the graph of tangent look like at that point, well, I know, okay, that tangent of theta is equal to sine of theta divided by cosine of theta, okay? So what I can do is I can look at the graphs of sine and cosine, and I can take the height of sine, okay, which is given by this orange curve here, and I can then divide it by the height of the cosine graph, okay? And the major issue that we recognized with this process okay, is that we are going to run into some major trouble at values of x, which cause cosine x to be equal to 0, because cosine x is our denominator. Okay, so when cosine x is getting close to 0, sine will be taking a value which is either 1 or -1. And that's going to cause our graph to have a vertical asymptote. Okay, so any x value which produces cosine of x equal to 0 is going to be a vertical asymptote. Okay, so looking at the graph of cosine x here, I can see that we pass through the x-axis at 3 pi over 2, at pi over 2, at negative pi over 2, and so on and so forth. So at every interval of pi, basically, but offset from the origin by pi over 2. Okay, so that was the last thing that we talked about, and I kind of had to rush through this last concept, which is, okay, well, what does the graph look like in between these vertical asymptotes, and which ones, what's the behavior near them? So here's what the behavior is. Okay, let me erase this, and we'll go back through it. Okay, so let's first figure out what's happening to the tangent graph in between negative pi over 2 and pi over 2. Okay, so let's focus in on this region, and let's start on the left side of the region and consider what's happening to the graph of the tangent function when x is very close to negative pi over 2. Okay, so this is still kind of what we were talking about last time, but I'm going to zoom in a little bit and do this a little bit more slowly. Okay, so as our x value marches leftwards towards negative pi over 2, the value of cosine is getting very, very close to 0, but positive. Okay, and the value of sine of x is getting very, very close to -1. So the way I would write this out using limit notation, which we've talked about a couple times, we would write something like the limit as x approaches negative pi over 2 from the right. Okay, so that's what that plus means there. Of sine of x over cosine of x. Okay, and I'm going to do something here that's not totally mathematically rigorous, but I'm going to say that sine of x is getting really, really close to -1. And I'm going to say that cosine of x is getting very, very close to 0, but still positive. So sometimes what I like to write is I'll write something like positive small here. Okay, and what I want to consider really when I'm taking this limit is what is happening to the value of this fraction when I divide the number -1 by a very, very small positive number. Well, if I take -1 and I divide by 0.1, I get -10. Or if I do -1 and I divide by 0.00001, I'll get something like -10000, or something like that. Okay, so we can see that what's happening is as we divide by a smaller and smaller and smaller positive number, okay, then the value of this limit is going to -infinity. Okay, so that is why when I drew the graph of the tangent function, okay, we have an asymptote here at negative pi over 2, and the behavior to the right side of the asymptote is that we're going down to -infinity. Okay, and if you don't like the limit notation, okay, if you don't like talking about things in this way, that's fine. You can use what the book does, and you can use the the notation that was something like, I don't know, f of x goes to blank as a goes to blank from the right or something like that. No, as x goes to, they actually use the a to the left and a to the right notation. So they use like a to the minus and a to the right. You can also, if you don't like evaluating these limits and really taking this kind of geometric approach, then you can always consider sine of x over cosine of x to be like a rational function, and just consider this cosine of x to have basically multiplicity 1 in the denominator, okay, to the 1. And then you can go back and look at, let me see if I can find it. It's been a minute since we talked about rational functions. Maybe that's not even far back enough. Week 7? No, before week 7 even. Hang on, let me find this. Oh, we're getting close now. Here it is. You can go back and look at these asymptotic behaviors, which we talked about with rational functions. Okay, so before we were considering, well, what is the sign of basically the rational function if we exclude the 0 in the denominator, okay? And that was our a. We checked whether a would be positive or negative, and whether the multiplicity of the 0 is odd or even. Okay, so for tangent, it's sine over cosine, so the denominator is cosine, so we would consider that 0 to be of odd multiplicity with multiplicity 1. Okay, so we're going to get one of these situations at either side of our tangent function. Okay, so that's another way you can view it if you don't like thinking about these limit processes. Okay, I just want to provide that as an option because, strictly speaking, this limit notation is not included in the book. Okay, so it's a little bit extracurricular. Okay, so that's how we determine what is happening in this kind of pink box region of this graph here. Okay, and then, well, if we want to check what's happening as we approach 0 from that region, so we're now going to consider, well, what happens to the graph of this thing as x marches along from negative pi over 2 to 0? Well, the value of our numerator gets closer and closer to 0, and the value of our denominator gets closer and closer to 1. Okay, and then once we're at the x value, x equals 0, then our numerator will be 0 and our denominator will be 1. Okay, so this is why our graph looks like it's coming right up straight to the origin here. Okay, I was going to have this kind of curve by nature of how the asymptotic behavior works with both of these two right sides. Okay, but this is generally where we're going, is we need to connect this asymptotic behavior down here to the left with this point which it crosses right through this origin here, okay, with a smooth curve. And then on the right side, we're going to see in a second that we're going up in this direction. Okay, so let's check. Well, as we go marching along on the x-axis from 0 to pi over 2, well, the value of our cosine graph is getting very, very close to 0, but positive. and the value of sine of x is getting very, very close to 1, which is a positive number. So if we divide a positive number like 1 by an extraordinarily small positive number, we'll get an extraordinarily large positive number. And we can see that the smaller number we get, the larger that number will be. And so that's why we can kind of see that as we get very, very close to pi over 2 here, what's going to happen is the value of our tangent function is going to go to infinity. Okay? So this is why we have this this asymptotic behavior up in this region on the right. Okay, and from here I'll leave it for you guys to check that what's going to happen is actually, because of the multiplicity of these zeros being 1, we're essentially going to have opposite behavior on both sides of these asymptotes. Okay, so when we go up on the left side, we have to go down on the right side, and it's going to look like a repetition of this graph on either side. Well, since the multiplicity is 1, we should have opposite end behavior on both sides of this asymptote, negative pi over 2. So since we're going down on the right side, we should be going up on the left side. So again, we get something which looks like this. Okay, and then so on and so forth as we go left and right. Okay. One final comment on the graph of the tangent function, which I want to remind you guys of, and this is something that I don't always see taught in pre-calculus classes. Okay, is the following. So we said originally when we developed the trigonometric functions, okay, that if we take some angle theta, okay, well, it has a point on the unit circle, and this distance here will be cosine of x, or cosine of theta, sorry. And this distance here will be sine of theta. So that the point on the unit circle is the point x comma y, which is equal to cosine of theta comma sine theta. That was how we defined sine and cosine. And the way we defined the tangent function, okay, was to be the ratio between these two values, okay, y divided by x. Okay, so we said, well, tangent of theta is equal to y over x. Or you could say it's equal to sine theta divided by cosine theta. And that was the way that we kind of wrote it down analytically. But I want everyone to just briefly recall that we actually also had a geometric interpretation of the tangent of this angle. It was to be the length of the tangent line, which comes in, okay, and it would be the length of this solid part of this tangent line, which comes at an angle and just barely touches our point, our circle at this one point, and then goes on and on until it touches the x-axis. And we said that the tangent of theta is actually going to be the length of this line segment, which connects the point on our unit circle to the x-axis. Okay, so for something which is for some angle theta, which is very, very close to 0, okay, we would get a point on the unit circle right here, and the tangent line would look like, you know, really, really short. Okay, so we can imagine that tangent should take a value 0 for an angle which is close to 0, or which is actually equal to 0. And then what happens to this line as our angle theta gets really, really close to pi over 2? Well, the length that it's going to take this line to go and then, you know, reach the x-axis is going to be very, very long, okay? So this is why we can imagine that as we go up to pi over 2, and in fact, when we hit pi over 2, the line, which is tangent to our circle, is actually going to be a horizontal line. Okay, so the reason that tangent is undefined when theta is equal to pi over 2 is that this, you could view it as, well, if you ask the question, what is the length of the line segment which connects this line to the x-axis? Well, it's sort of nonsensical since it doesn't ever cross the x-axis. It's parallel. Okay, so that's one extra layer of intuition that you guys can have for the tangent function. Okay, I think I've been monologuing for a while now. Let me check in with you guys. How do we feel about the graph of this tangent function? Do we feel comfortable with this, totally confused by this, or somewhere in the middle? Maybe we could have like a 1 through 10, 1 being least satisfied and 10 being most satisfied. Okay, so some middling results and some higher results. Okay. I would say my recommendation to you all would be, I think, well, yeah. In my opinion, I think the simplest way to think about what the graph of the tangent function should be is to consider the division of the heights of these two functions, okay? So at a given point, we just take the height of the sine function and we divide it by the height of the cosine function, okay? And, you know, at places where sine is positive and cosine is 0, well, we're going to, on the left side, be going up, and on the right side, be going down, okay? And that's kind of the best intuition that I can think of for these guys. But this is another nice way to think about it in terms of, you know, you can just kind of think of this tangent line as coming in and just barely touching our circle here at some point, and then you can imagine, well, what is this distance here which goes between that point on our unit circle and the x-axis? That's the other way to think about it. Okay, so ultimately we wind up with a function which is actually repeating on a shorter time period than we're used to seeing. Okay, it turns out that the height of a point on the tangent function is the same as the height of points which are a certain distance away. Okay, and this distance now, rather than being 2 pi, like how it was for sine and cosine, it turns out to be just pi. Okay, so tangent is a pi periodic function. And if you want to see why that's true from looking at the graph, okay, then you can see that what's going to happen is essentially, how can I take this most easily? If we consider this x value here, okay, where cosine is above the sine function, okay, and we consider a point which is pi units to the right of that, okay, so that would be like somewhere here. Okay, then we can see that although both of our functions are now in the bottom half of the coordinate plane, whereas they were both in the top half of the coordinate plane. The ratio between the heights, hang on a sec. Yeah, the ratio between the heights will be the same. Okay, because in the first case, we're sort of taking a positive number and dividing by a positive number. And in the second case, we're taking that same positive number, except we're taking it negative, and we're dividing by the same cosine value, but negative. So this is why we're going to see the same ratio. Okay. All right, I don't want to overload you guys with that. I'll talk a little bit more about periodicity of the tangent function later on. But first, let's learn, well, how can we graph these other trigonometric functions like cosecant, secant, and cotangent, okay? And I'm going to go through these a little bit quicker, okay? So I know that cosecant of x, remember, is 1 over, maybe somebody can tell me what should go in this denominator here such that this is going to be true. It should be another trigonometric function, and we invert it to get cosecant. That's right. Home Kumar's got it, which should be sine of x. Okay, so don't forget, we have to remember that this is not how we think it should be. Okay, the cosecant is 1 over sine, and the secant is 1 over cosine. Okay. All right. So here's what I'm going to do. I'm going to draw sine of x, and then we're going to consider, well, what do we think 1 over that is going to look like? Okay, so sine of x comes through 0. It reaches a maximum at pi over 2, and then it goes through at pi, and then it reaches a minimum at 3 pi over 2, and then it's back at 0 at pi. 2 pi, sorry. Okay, so if we want to know what the graph of cosecant looks like, we want to consider, well, what is the height of the function if the height of the function is given by 1 divided by the height of this function? So I'll do that in orange, maybe. Okay, well, as we approach 0 here, coming down here, the denominator of our function is going to be positive and getting close to 0, and the numerator of our function is a positive number. So we can imagine that cosecant of x should be blowing up here. Okay, it should be getting close to infinity. All right, and it turns out, okay, if we want to consider, well, what is the minimum value that this function could take? Well, if we have a fraction here, the fraction is going to reach a minimum when the denominator is largest. Okay, so we know that the function cosecant of x is going to reach a minimum when sine of x reaches a maximum. And sine of x reaches a maximum at the point pi over 2, or at the x value pi over 2. And the value of sine at that point is 1. So we know that when x is pi over 2, then cosecant of x is going to be cosecant of pi over 2 is going to be equal to 1 over sine of pi over 2 is going to be equal to 1 over 1, which is just 1. Okay, so we should reach a minimum down here at 1. And then again, as I go marching along my x-axis towards pi, the denominator is becoming very, very small and positive. So what's happening is I should imagine this thing comes down and reaches this minimum here, and then our denominator goes to 0, and we go up again. Okay? So that's what's going on there. And then we're going to have slightly different behavior happening for the region where we're negative. It's just going to look the same, except it should be negative. Okay, because we take 1 and we divide it by a negative number, we're going to get a negative number. Okay, so we again have asymptotes. Okay, this time instead of being at negative pi over 2 and pi over 2, we have them at 0 and pi. Okay, and then again, if we were to extend sine out in this direction, it looks something like this. Okay, and then our cosecant graph is going to look like this. And then like this. Okay, and so on and so forth. Okay, so we get these asymptotes every pi units, but it's not a pi periodic function because we can see that although we have an asymptote every pi units, the behavior alternates between each pi region, and we only repeat every 2 pi units. Okay, so in this case, if we want to measure the period of this function, well, we take a look at a point here, and we measure this distance, which goes from that point to the next point with that same direction and height, and we would measure that as 2 pi units in this case. Okay, and that comes from the fact that sine of x is a 2 pi periodic function, so sine of x takes the same value for any two values of x which are 2 pi units apart. So cosine of x, which is 1 over sine of x, does the same thing. Okay. Now, let me ask, before we try to graph 1 over cosine of x and secant of x, let me ask you all a question. The question is the following. Is there a relationship between the graph of sine of x and the graph of cosine of x? And then, oh crap. Let's see, it reaches the maximum here and then goes down and then so on and so forth. Is there a relationship between these two graphs here? Okay, so our blue graph is cosine of x. We want to know, is there a relationship between the graph of cosine of x and the graph of sine of x? Yes. Okay, I think that's a good answer. Can you elucidate what the relationship is between these two? Very good. Yeah, that is probably as concisely as I could have been possibly put. The graph of cosine x looks like the graph of sine of x, which just got shifted over by pi over 2 units. So, I don't know. I don't think there's going to be a way for me to select all of this. But if we were to move this entire thing over pi over 2 units, you're right, they would overlap. Okay? So if we want to know what does the graph of 1 over cosine look like, we might expect that it looks a lot like the graph of 1 over sine, except moved over, as you say, pi over 2 units. Okay, so it turns out that the graph of 1 over cosine of x is going to look a lot like this, except it's going to be moved over use orange again, except it's going to be moved over by pi over 2 units. So here's 1 and here is -1. So what does this one look like? Well, instead of reaching a minimum at pi over 2, it reaches a minimum at 0. And it's got an asymptote every pi units, but they're offset a little bit from the ones that were not every pi over 2, every pi units. But they're offset from the ones which we had for 1 over sine by pi over 2 units. Okay, so then again, down here, we're going to look like this. And then so on and so forth. Okay, so in this case, we're again 2 pi periodic by virtue of the fact that cosine of x is 2 pi periodic. And the graph of it has the same relationship to the graph of cosecant of x as cosine has to the graph of sine of x. Okay, so we still get that relationship preserved. Okay, so this is how we graph 1 over cosine of x. And then for cotangent of x, well, I'm just going to remind us that this is equal to 1 over tangent of x whenever tangent of x exists. Well, what does tangent of x look like? It looks like it comes down from the bottom and goes up to here. Oh, I should have used another color, sorry. This is not good practice. Should go back to our pink. 1 over tangent of x. So for tangent of x, I'm going to draw it in here. Tangent of x looks like this. So if I want to know what does 1 divided by this look like, well, when the number gets really, really close to negative infinity, 1 divided by it is going to be really, really close to what? 0? And then when the value of tangent gets very close to 0, but less than 0, we're going to be going down to infinity. And then on the right side, we'll be going up to infinity. And again, looking kind of like this, I think. Okay, so the places where tangent of x is going to infinity, we have cotangent of x is going to 0. And the places where tangent of x is going to 0, we have cotangent of x going to either positive or negative infinity. Okay. And, okay, I suppose I should, to be really clear about cotangent, okay, I should specify that this isn't the exact definition of cotangent. This is what it will be whenever tangent of x exists, and there's one point where tangent of x doesn't exist, okay? And that's, well, there's infinitely many points, but it will be these points where we go to infinity, okay, where tangent of x is undefined. In those regions, the way we have to define cotangent of x is by looking at the unit circle and saying, well, if this is the point x comma y, then cotangent of x is defined to be the ratio x over y. And this will be defined at these points where tangent of x is undefined. Okay, so even if x is 0, then the ratio x over y will still be defined, whereas the ratio y over x, which is tangent of x, will not be defined. Okay, so these are how we kind of come up with these graphs of these different trig functions, okay, these cosecant, secant, cotangent, and tangent, we kind of derive their graphs from the graphs of sine and cosine. And then, well, the last one, cotangent, we sort of derived it from the graph of tangent. Okay, so all we want to do is imagine these different ratios of these heights of those functions at a given x value, and we plot the ratio as the height of our new function. Okay? Let me pause and ask, are there any questions over this material so far regarding the graphs of the more non-standard trigonometric functions? Okay, there is a question in here. Let's see. Can cotangent of x cross the vertical asymptote, or is that only for tangent? Aha, I think you're referring maybe to these pink vertical asymptotes. This pink x equals pi over 2 is a vertical asymptote for tangent of x, but not for cotangent of x. And at the risk of making our graph even messier, I'm going to draw in the actual asymptotes for cotangent will be offset again by a measure of pi over 2. So cotangent of x also has vertical asymptotes. It's going to have a vertical asymptote at the values of x which cause tangent of x to be equal to 0. Okay, that's where we're going to have a vertical asymptote for cotangent of x. I'm trying to kind of like split the graphs here between like, okay, the pink is the function of what we used to have, and the orange is going to be the function of our new function, which we get from the ratio. How I was trying to split it anyways. Okay. Thanks for the question, Savannah. Are there any other questions on these graphs and how I came up with these? Okay, seems like not. Okay, so let me return briefly to our discussion about the periodicity of the tangent function. Okay, so here's a diagram showing maybe why tangent is going to be pi periodic rather than 2 pi periodic. And it's going to use the argument, which is based on this kind of geometric interpretation of tangent as being the distance from that point, which goes straight to the x-axis in the direction of the tangent line, which comes in and just barely kisses our circle at one single point. Okay, so if we imagine the tangent of theta to be this length here on the right side, okay, and if we draw in instead the angle theta plus pi, well, theta plus pi goes in the exact opposite direction as what theta went in. And if we draw the point which is on that unit circle and imagine the distance that it takes us to go from there to the x-axis, we can imagine why that distance will be the same as the distance that it took us to go to the x-axis on our other side. Okay, and this will work for any 2 points which are exactly across from one another, okay, oops, that's definitely not across, which are exactly across from one another on our unit circle. We're going to have a long one here. Well, we're also going to have a long one here. Okay, and so on and so forth. So this is why tangent takes the same values in these 2 points. And there's another way that you can kind of think about it, and that would be to use ASTC. Okay, so if you consider what happens to sine in all of these different regions, well, we're positive, then negative, then negative. So the time it takes us to get back to being positive, okay, as we start positive and then we go negative, and we're not positive again until we get all the way back to our first quadrant. So that's why sine is 2 pi periodic. But if you consider what's happening with tangent, tangent alternates on a every other basis. We go positive, negative, positive, negative. So it turns out that the values of tangent are going to be the same in quadrant 1 and 2, and they're going to be the same in quadrant, I'm sorry, not 1 and 2, 1 and 3, and then they would be the same in quadrants 2 and 4. So that's another way that you can think about it using the ASTC as kind of your basis of thought. Okay, so 3 ways to think about it being pi periodic. We can think about the ratio between those 2 sine and cosine functions. We can think about what tangent really means geometrically. And we can think about ASTC. Okay. And then as for why we should expect cotangent of theta to be pi periodic, well, it just comes from the fact that tan theta is pi periodic. So we have the property that tan theta is equal to tan of theta plus pi. So if we do 1 over tan theta, that's going to be equal to 1 over tan theta plus pi. So we get that cotangent of theta is equal to cotangent of theta plus pi. Okay. So, if I'm not mistaken, I might have, no, it doesn't look like I did. I will add a page in here and really quickly comment on the periodicity of each of these functions. Let me go back and use a different color. Use pink. Okay, so let's write down each trigonometric function and state its period. Sine of x, the period is 2 pi. Cosine of x, the period is 2 pi. Tangent of x, the period is pi. Cosecant of x, the period is 2 pi by virtue of the fact that cosecant comes from sine, and sine is 2 pi periodic, so cosecant will be 2 pi periodic. Secant x, 2 pi periodic, again for the same reason as before. Secant of x comes from cosine of x, which is 2 pi periodic, so secant will also be 2 pi periodic. And cotangent of x comes from tangent, so it'll be pi periodic. Okay, so there's only 2 real outliers here. It's tangent and cotangent. Those are the pi periodic ones. And those are because those are the ones that, you know, we have that kind of ASTC relationship where it's alternating every quadrant rather than every half of the entire coordinate plane. I don't know what you call that. Half space, maybe. Okay. Any questions about these kind of brief comments on the periodicity of all of our trigonometric functions? All right. Well, one thing that I'll just tell everyone briefly, okay, is that really for all of these things that I'm explaining about these trigonometric things, okay, for most topics, I'm sort of trying to give like 3 or 4 different ways of thinking about them, okay? So, you know, if you're in the class, I don't want you to be super overwhelmed by all of these, but what I'd like you to do is find whichever one resonates with you, you know, for each topic and maybe latch onto that. So if you really like viewing things in this sort of, you know, more algebraic or analytic kind of like way, can you like writing out the functions and working with the definitions, then great. If you like considering geometrically what all this stuff looks like on the unit circle, then that's also great. Okay? And if you want to imagine the relationship between the graphs of certain functions and other functions, that's also fine. Okay? You just need to make sure that you have, you know, for basically for each topic, you have one way that you know how to kind of approach these topics. And, you know, it can be tough to pick which one to approach it with, but that's also where you can kind of, you know, be a little bit creative with this math stuff. I want to say I was reading the other day that David Hilbert, a famous mathematician, once had a student who dropped out of his mathematics program to become a poet. And David Hilbert wasn't really that nice of a guy, and he said, well, that's good. He wasn't creative enough to be a mathematician. So anyways, not sure I agree with David Hilbert's methodology there. But, you know, it is to say that essentially there are a lot of places in math where, you know, you have an opportunity to be a little bit creative and use your own approach. And trigonometry is definitely one of them. There's a lot of connections here. Okay. Well, maybe we'll move on. I'll get off my soapbox. Okay, so let's do a couple practice problems, and I think we're probably not going to make it to inverse trig today. But let's try a couple practice problems, like something that I could, you know, give on an exam or a homework. Okay, and just try to work with all of these. Okay, so the first problem is we want to find a value b so that the function secant of b times x is pi over 3 periodic. Okay, so let me remind ourselves why we might expect the period, okay, the period of a function to change when we multiply on the inside by a number. Okay. All right, so here we've got the functions sine of x in purple, okay, and the function sine of 2x, okay, in blue. All right. So what we might remember from when we started the class, okay, is that when we multiply by a number on the inside, okay, depending on whether the number is larger than 1 or less than 1, Okay, it's going to correspond to a horizontal stretch or a horizontal compression. Okay, so you can think of this sine wave as kind of like a slinky, and we're either going to pull it out and stretch it out, or we're going to push it in and compress it. Okay, so this is definitely going to have an effect on the period of our function. Remember, the period of the function was defined in our class to be the distance between the crests of the waves. And we can see that the distance between the crest of the first purple wave and the crest of the second purple wave is something like, I don't know, 2 pi units. Okay, and it looks like the distance between the crests of the blue waves is much shorter, right? We can see that this has had an effect on the period of our trigonometric function. Okay, in fact, we even commented on what the periodicity would be when we have a bx on the inside. But let's approach this from maybe a more analytic perspective. Okay, so I'm going to step away from geometric interpretations for a minute. Okay, and consider the following. Well, what does it mean for a function to be pi over 3 periodic? It means that if I plug in an x value versus if I plug in that same x value plus pi over 3, then the function is going to give me the same value for each of these. So let's try it. Well, if I plug in, and I want the following relationship to be true, I want sine of b times x to be equal to, sorry, secant of b times x. I want that to be equal to if I instead plugged in not x, but x plus pi over 3. Okay, and I do need to remember to treat this as its own number such that it should be multiplied entirely by the b. Okay, so this is the relationship that I want to be true. Okay, this is the relationship that I want to be true. And, you know, personally, I find it sometimes a little bit daunting to work with the secant function. So rather than working with the secant function, I'd rather work with what the secant function is defined by, which is cosine. So I'm going to rewrite this and write 1 over cosine of bx should be equal to 1 over cosine of b times x plus pi over 3. Okay, and I have two fractions here with different denominators, but same numerators. So I know that this equality will only hold if the denominators are equal to one another. So I can write cosine of bx is just equal to cosine of b times x plus pi over 3. And I want this to be true. Okay, I want this statement to be true. So let me ask you guys, is there something that I know about the cosine function which I could use to approach figuring out what this value b should be that's going to make this statement true for any value x? Any properties of cosine that could be useful here? Yeah, I think you're on the right track, Abdul Rahman. You're gonna get there, but I'm looking for just, you know, just a little piece of the puzzle at this time. You gave me the full ending there. Can you tell me which property of cosine you used to eventually wind up at that spot? Oh, okay, use the formula. That works too. Yeah. Okay. Well, let me explain where that actually comes from. Okay, we know the following is true. We know that, so this will be a side note, we know that cosine of x is always equal to cosine of x plus 2 pi. That was what it meant for cosine of x to be 2 pi periodic. Okay, so if we have sine of bx being set equal to sine of bx plus some other stuff, then essentially the other stuff ought to be equal to 2 pi, is kind of what I'm going to say here. So I'm going to expand that inside of that right-hand side function. So I have sine of bx is equal to, cosine of bx is equal to cosine of bx plus b pi over 3. And I want to reconcile these two facts. The fact that cosine of x is always equal to cosine of x plus 2 pi. Well, here I have cosine of bx is equal to cosine of bx plus some other stuff. Well, what I'm trying to say here is that we have the same thing here and here, and then we add something to the angle on the second case. And these should always be equal. Okay, and by virtue of the fact that cosine of x is 2 pi periodic, we should expect the following relationship to hold. This statement will always be true if b times pi over 3 is equal to 2 pi, because cosine is 2 pi periodic. Okay, so if we take some angle and then we add 2 pi to it, well, the cosine of that function will still stay the same. Okay. Okay, so if b pi over 3 is equal to 2 pi, then these things will be equal. So we get b should be equal to 2 pi times 3 over pi. Cancel the pi's, and we get 6. Okay. All right, so, what have I really done here? I've just essentially taken a look at this in a very mathematical way, just kind of looking at what is the definition of pi over 3 periodicity, and using some facts which I already knew about the periodicity of other trigonometric functions to get to where I wanted to be. Okay. Now, if you wanted to, you could also take another approach on this problem. Okay, so if you don't like this approach, you don't like working with these definitions and with these trigonometric functions in a kind of hands-on way, well, you could give a more loosey-goosey argument depending on the graph of this function. Okay, and here's what I'll say. I'll say here we have cosine of x. I know that cosine of bx is essentially going to be either stretched or compressed, depending on the value of B. Okay, so if we compress a periodic function by a factor of B, then the period will be scaled by a factor of B. And then we could say, well, if we want our scaled function to be pi over 3 periodic, okay, so we want our period to go from 2 pi, we want our period to go to pi over 3. And we know that this should be compressed by, we compress a periodic function by a factor of B. Period will be scaled by a factor of okay, I shouldn't have said this. I said this is going to be this should be a horizontal compression of a periodic function by a factor of 1 over B. The period will be scaled by a factor of 1 over B. Sorry. That comes from the fact that the B is on the inside. We got to remember that this is going to scale us horizontally by a factor of 1 over B. Okay, so really I want 2 pi to be scaled down to pi over 3 by this factor of 1 over B. So what I really want is that 2 pi times 1 over B should be equal to pi over 3. That should be my new period. Okay, and then if I just solve this, then I get B times pi over 3 should be equal to 2 pi, and then I divide the 3 over pi, so we get B is equal to 2 pi times 3 divided by pi, therefore B is equal to 6. Okay, that was a struggle. But that's another way you could think about it, okay? So if you want to view this more geometrically, you know, this is an argument which I feel would be more than satisfactory on a homework or on an exam. Okay, if you want to use this information, that's also fine. Okay. So just curious, let me ask you guys, does anybody have a strong feeling that one of these methods is better than the other? Prefer the second method a lot more. Okay. So maybe you feel like you're more of a visual learner, you like the geometric interpretation. Okay. All right, well, at this point, I'm a full, I think, 2 days behind. And of course, I still haven't even finished this section. But I think we'll start in on inverse trig next time, and that'll be kind of motivated by these questions of whether these functions are one-to-one. Okay, so we'll talk about whether these functions are one-to-one next time. And of course, one-to-oneness is going to tell us when we have an inverse function. Okay, so that's what we'll talk about next time. I think I'll close here for today. If you have any questions, feel free to stay after class. I know I kind of threw a lot at you guys today. So if you're confused, make sure you come to office hours tomorrow. I've got 2 full hours of office hours tomorrow. for you guys to come to. So hope to see some of you guys there. Some other students were here in office hours yesterday, and we had a good discussion. So yeah, otherwise, everybody have a great day, and I'll see you guys tomorrow.
Those are all the stickers that people put on their door. So when you walk in, yeah.
Yep, thanks, Heidi, you too. If you guys have any questions, of course, we can stay after class for a few minutes. Oh, Sam, looks like you had a question there that I didn't quite get to. So the example was tangent instead of secant. Then b pi over 3 be equal to pi instead of 2 pi. Yes. You are exactly right, Sam. It would be equal to pi instead of 2 pi. Yep, that just comes from the fact that, right, tangent has a period of pi, so if you want to scale it, yep. Yeah, very good. Yep, you too.